From the smartphone in your pocket to the supercomputers driving AI, every facet of modern life is powered by tiny, intricate devices, semiconductor chips. These aren't just components, they are the invisible engines of our digital world, controlling everything from communication to defense systems. Yet, the true marvel isn't just their existence, but the almost incomprehensible process required to create them. We live in a world utterly dependent on these silicon brains, a dependency that has quietly reshaped global power dynamics and made their manufacturing the most contested industry on Earth. At the heart of this manufacturing miracle stands a machine unlike any other, a technological marvel so complex and costly that it redefines the limits of engineering. This is the extreme ultraviolet, or EUV, lithography system, developed by the Dutch company ASML. Each one is a multi-story, $200 million behemoth, weighing hundreds of tons and comprising over 100,000 components. It is not merely a machine, it is a factory unto itself, a testament to human ingenuity pushed to its absolute breaking point, capable of etching features unimaginably small. But even the most advanced tools require skilled hands. The true masters of wielding ASML's EUV technology are found in Taiwan, at Taiwan Semiconductor Manufacturing Company, or TSMC. TSMC isn't just a chip manufacturer, it is the world's most critical semiconductor foundry, producing over 90% of the world's most advanced chips. Their symbiotic relationship with ASML forms an unbreakable nexus at the very forefront of technological progress, and its strategic importance to global supply chains cannot be overstated. It's the critical link in the chain. This convergence of unparalleled engineering and manufacturing dominance has created an unprecedented geopolitical choke point. The ability to produce these most advanced chips is concentrated in the hands of very few, primarily ASML and TSMC, making this single, ultra-complex manufacturing technology the focal point of a global technological arms race. Control over this capability translates directly into economic power, military advantage, and national security. Understanding this machine is to understand the future of global power dynamics. To appreciate the scale of ASML's achievement, we must first understand the fundamental challenge of semiconductor manufacturing: miniaturization. Decades ago, chips were relatively large, housing thousands of transistors. Today, a single chip can contain billions. Each transistor acts as an on-off switch, controlling the flow of electrons, and the more you pack onto a chip, the faster, more efficient, and more powerful the device becomes. This relentless drive to shrink components is what defines Moore's law and powers our technological advancement. The primary method for creating these minuscule features is called lithography, derived from the Greek words for stone and to write. In essence, it's a photographic process. A pattern is projected onto a silicon wafer coated with a light-sensitive material, much like developing a photograph. The challenge, however, comes with the size. To etch smaller features, you need light with a shorter wavelength. Imagine trying to write a tiny letter with a blunt crayon, it's impossible. You need a sharper, finer tool. This principle became the ultimate barrier for traditional lithography. For decades, chipmakers relied on various forms of ultraviolet, UV, light. Early machines used light at wavelengths of 365 nanometers, then 248 nanometers, pushing the limits with each generation. Around the turn of the millennium, deep ultraviolet (DUV) lithography, using excimer lasers at 193 nanometers, became the industry standard. But even 193 nanometers was becoming too broad a brush to paint the nanoscale features required for the next generation of chips. A fundamentally new approach was desperately needed, one that seemed almost impossible. By the mid-1990s, the semiconductor industry faced a looming crisis. Moore's law, the exponential growth in chip performance, was threatened by the physical limitations of DUV lithography. Scientists and engineers around the world scrambled for solutions, exploring exotic light sources and revolutionary new optics. The industry understood that without a breakthrough, the relentless pace of innovation would stall, impacting everything from consumer electronics to scientific research and defense. The stakes were incredibly high, promising colossal rewards for anyone who could solve this seemingly insurmountable challenge. Enter ASML. Founded in 1984 as a joint venture between Dutch electronics giant Philips and chip equipment maker ASM International, ASML was a relatively small player in a field dominated by giants. Their early days were fraught with challenges, operating out of a leaky shed in Veldhoven, Netherlands. Many doubted they could compete with established rivals. Yet, what ASML lacked in initial resources, it compensated for with an audacious vision and an unwavering commitment to solving the toughest problems in lithography, a commitment that would eventually redefine the industry. While other companies explored multiple paths, ASML made a singular, monumental gamble: extreme ultraviolet (EUV) lithography. This technology promised to reduce the light wavelength from 193 nanometers to a mere 13.5 nanometers, a reduction by a factor of over 14. This wasn't an incremental improvement, it was a quantum leap. The challenges were immense, bordering on science fiction: how to generate such light, how to focus it, and how to operate within an environment where even air absorbs this ultra-short wavelength. It was a multi-decade project, consuming billions of dollars in research and development. The first, and arguably greatest, hurdle for EUV was generating the light itself. Conventional light sources simply wouldn't work at 13.5 nanometers. ASML and its partners realized they needed to create a plasma, an ionized gas, so hot that it would emit light at the desired wavelength. The solution they painstakingly developed involves a complex choreography of tin droplets and powerful lasers. This process is so precise, so energetic, and so finely tuned that it remains one of the most astonishing feats of engineering. Imagine a stream of molten tin, heated to over 200 degrees Celsius, falling at a rate of 50,000 droplets per second. Each droplet is smaller than a human hair, about 30 micrometers in diameter. These droplets are precisely targeted by two separate lasers. The first, a low-power pre-pulse laser, flattens the spherical droplet into a pancake shape, optimizing it for the next step. This seemingly simple action is critical for the efficiency and stability of the entire light generation process, demonstrating ASML's fanatical attention to detail. Immediately after the pre-pulse, a high-power CO2 laser, emitting 20 kilowatts of light, strikes the now flattened tin droplet. This main pulse delivers an incredible jolt of energy, instantly vaporizing the tin and creating a superheated plasma that reaches temperatures of over 200,000 degrees Celsius. At this extreme temperature, the tin plasma emits a burst of 13.5 nanometer EUV light. This entire process, from droplet formation to EUV emission, occurs within a few millionths of a second, repeating tens of thousands of times per second. Such a violent process generates not only EUV light but also a significant amount of tin debris, which can quickly coat and damage the delicate optics of the machine. To combat this, ASML employs a crucial and ingenious solution: a collector mirror coated with ruthenium. This mirror focuses the EUV light, but also utilizes an electric field to repel charged tin ions, protecting its surface. Additionally, a hydrogen plasma is used to continuously clean the mirror, evaporating any tin that might accumulate. Without this debris control, the entire system would fail within minutes. Once generated, EUV light presents another immense challenge: it cannot be transmitted through glass lenses like conventional light. At 13.5 nanometers, virtually all materials, including air and glass, absorb EUV radiation. This meant that the entire optical system had to be completely reimagined. Instead of refractive lenses, ASML, in collaboration with Carl Zeiss SMT, developed a system of highly specialized mirrors. These mirrors, polished to unimaginable precision, are the only way to steer and focus the EUV light onto the silicon wafer. These mirrors are not just reflective surfaces, they are masterpieces of optical engineering. Each mirror is coated with alternating layers of silicon and molybdenum, precisely 40 to 80 atomic layers thick. This multi-layer coating reflects approximately 70% of the incident EUV light, a staggering achievement given the nature of EUV. To maximize reflection, the surface must be flawlessly smooth. If one of these mirrors were scaled up to the size of Germany, the largest imperfection would be no bigger than a single atom. This level of precision is utterly mind-boggling. Because even air absorbs EUV light, the entire path of the light inside the ASML machine, from its generation to the wafer, must be kept under an extreme vacuum. This means the enormous machine operates with internal chambers where the pressure is millions of times lower than atmospheric pressure, similar to the vacuum found in outer space. Maintaining this vacuum while managing thousands of moving parts and ultra-precise positioning systems adds another layer of complexity to the already intricate design. It's a cosmic environment contained within a factory floor. Just as in traditional photography, a negative or photomask is used to project the circuit pattern. For EUV, these masks are also reflective, rather than transparent. A critical component, only recently perfected, is the pellicle. This ultra-thin, transparent membrane protects the photomask from particles. If a dust particle landed on the mask, it would be etched onto every chip, rendering them useless. For years, the lack of a robust EUV pellicle was a major bottleneck, highlighting how every seemingly minor detail in this process can derail the entire system. The precision required within an ASML EUV machine is almost beyond human perception. The wafer stage, which holds the silicon wafer, must position it with an accuracy equivalent to aiming a laser from Earth to hit a specific dimple on a golf ball on the moon. Any vibration, even footsteps from someone walking nearby, can disrupt the process. This demands extreme vibration isolation, temperature control down to millikelvin ranges, and active compensation systems that make constant, minute adjustments. It's a dance of subatomic precision. To protect these sensitive processes, ASML machines operate within pristine cleanroom environments, often class 1, meaning fewer than one particle of 0.5 micrometers or larger per cubic foot of air. This is orders of magnitude cleaner than a hospital operating room. Engineers wear full bunny suits to prevent shedding skin flakes or hair. The air is meticulously filtered and circulated. Even the act of opening a machine for maintenance requires a carefully choreographed procedure to maintain contamination control. It's an environment where every speck of dust is a potential disaster. ASML's success is not just its own, it's a testament to global collaboration. The company relies on a vast ecosystem of highly specialized suppliers worldwide, each providing a critical component or expertise. Zeiss SMT provides the mirrors, Cymer, now an ASML subsidiary, developed the light source, and companies from across Europe, Asia, and North America contribute everything from high-precision robotics to advanced materials. This interwoven supply chain makes ASML a truly global enterprise, and its vulnerability a global concern. After billions of dollars and decades of research, ASML finally delivered its first commercial EUV system, the TWINSCAN NXE3400B, in 2017. This was not the end of the journey, but the beginning of high-volume manufacturing. The initial systems faced challenges with uptime and throughput, but through relentless iteration and close collaboration with lead customers like TSMC, ASML rapidly improved performance. It was a race against time, as the demand for smaller, more powerful chips was insatiable, and the window for DUV was rapidly closing. Even as ASML perfected its initial EUV systems, it was already developing the next generation, high-NA EUV. Numerical aperture, NA, refers to the light-gathering ability of the optics, and a higher NA allows for even finer resolution and smaller features. The first high-NA EUV system, the TWINSCAN EXE5000, is designed to enable the production of 2-nanometer chips and beyond. This continuous innovation, pushing the boundaries of physics and engineering, ensures ASML's continued dominance and the ongoing advancement of Moore's law. It's a never-ending quest for the ultimate precision. While ASML built the tools, TSMC transformed how chips are made. Founded in 1987 by Morris Chang, TSMC pioneered the pure-play foundry model. Instead of designing and manufacturing its own chips, TSMC focused solely on manufacturing designs from other companies. This allowed chip designers like Apple, Qualcomm, and Nvidia to innovate without the immense capital expenditure of building their own fabs. This model democratized access to advanced manufacturing, fostering an explosion of innovation in the semiconductor industry. TSMC became ASML's most crucial partner in scaling EUV technology. As the largest customer, TSMC invested heavily in ASML's early research and was instrumental in providing feedback for continuous improvements. Their engineers worked hand in hand to integrate these complex machines into their fabrication lines, overcoming countless technical hurdles. Without TSMC's commitment and engineering prowess to adopt and optimize EUV for high-volume manufacturing, the technology might have remained a laboratory curiosity. They brought it to life at scale. Today, TSMC utterly dominates the production of the world's most advanced chips, specifically those built on 7 nanometer, 5 nanometer, and increasingly 3 nanometer process nodes. These are the chips that power the latest iPhones, high-performance computing, and cutting-edge AI. No other company can match TSMC's scale, efficiency, and technological lead at these critical nodes. This dominance makes TSMC an indispensable linchpin for global technology, providing the foundation for nearly every major tech company. The scale of TSMC's operations is staggering. They operate dozens of fabrication plants, or fabs, each costing tens of billions of dollars to build and equip. These fabs consume vast amounts of electricity and ultra-pure water. Thousands of engineers and technicians work tirelessly 24/7 in a ballet of automation and human expertise, overseeing machines that execute billions of precise steps. This colossal infrastructure represents decades of investment, specialized knowledge, and an organizational masterpiece dedicated to continuous, relentless manufacturing innovation. Taiwan's role in this ecosystem is not accidental, it's the result of decades of deliberate industrial policy, educational investment, and geopolitical circumstance. The island has cultivated a highly skilled workforce, a strong engineering culture, and a supportive government that understands the strategic importance of semiconductors. This environment allowed companies like TSMC to flourish, creating a powerful economic and technological moat around the island. Taiwan has truly become the Silicon Island, making it an irreplaceable node in the global economy. The concentration of advanced chip manufacturing in Taiwan has given rise to the concept of the silicon shield. This theory suggests that Taiwan's indispensable role in the global technology supply chain provides a deterrent against potential military action, particularly from mainland China. Any disruption to TSMC's operations would cause an economic catastrophe on a global scale, crippling industries worldwide and affecting virtually every nation. This interdependence acts as a powerful, albeit fragile, geopolitical buffer. The strategic importance of ASML's EUV machines in TSMC's fabs has thrown them into the center of the escalating technological rivalry between the United States and China. China, aspiring to be self-sufficient in advanced chip manufacturing, desperately needs this technology. However, the US, recognizing the critical leverage, has imposed stringent export controls, specifically targeting ASML's ability to sell its most advanced EUV and even DUV machines to Chinese chipmakers. This is a direct attempt to curb China's technological ambitions. The US campaign has been remarkably effective. Under pressure, the Dutch government has restricted ASML from exporting its most advanced EUV machines to China since 2019. More recently, these restrictions were broadened to include certain DUV systems, preventing Chinese companies from even building less advanced, but still crucial, chips without significant foreign input. This move effectively bottlenecks China's aspirations for technological independence, creating immense tension and forcing China to invest even more heavily in indigenous solutions. China's efforts to achieve semiconductor self-sufficiency are a monumental national priority, backed by billions of dollars in government subsidies. However, replicating ASML's 40 years of specialized research and its unique global supply chain is incredibly difficult, if not impossible, in the short term. While China has made progress in less advanced chip nodes, it remains years, if not decades, behind in producing the cutting-edge chips that power the most sophisticated technologies. The ASML choke point is proving profoundly effective. This geopolitical tension highlights the extreme fragility of the global chip supply chain. Any disruption, whether from natural disaster, geopolitical conflict, or even a targeted cyber attack on TSMC or ASML, would send shockwaves across the global economy. Companies, governments, and consumers worldwide would face. In response, nations like the United States and the European Union are pushing for reshoring or friendshoring chip manufacturing, investing massive sums to build domestic fabs. Intel, for example, is receiving significant government incentives to build new fabs in the US and Europe. While these efforts aim to reduce dependency on Taiwan and diversify the supply chain, building a cutting-edge fab takes years and tens of billions of dollars, and replicating TSMC's expertise in ASML's EUV dominance is an almost insurmountable challenge. Diversification is a long, arduous road. The $200 million price tag of an ASML EUV machine hints at the true cost of global technological control. It's not just the hardware, it's the decades of investment, the concentration of rare expertise, the intricate global supply chain, and the strategic partnerships that make these machines possible. This cost extends beyond economics, touching upon national security, geopolitical leverage, and the very foundation of modern civilization. The ability to control who gets these machines is the ability to shape the future. ASML occupies an almost monopolistic position in the most critical segment of chip manufacturing. No other company has successfully developed an equivalent, commercially viable EUV system. This makes ASML an unprecedented kingmaker in the tech world. Its technology is so foundational that access to it dictates which countries and companies can compete at the leading edge of innovation. This is not just a business advantage, it's a strategic weapon, making ASML a critical player in global power dynamics, far beyond its Dutch origins. The semiconductor race is far from over. As ASML develops high-NA EUV, and TSMC pushes towards 2 nanometer and 1 nanometer process nodes, the stakes continue to rise. Every incremental improvement in lithography and manufacturing efficiency translates into competitive advantage, economic growth, and potentially, military superiority. This relentless pursuit of miniaturization and power defines our technological trajectory, ensuring that ASML and TSMC remain at the very pinnacle of global strategic importance. The world waits to see what comes next. The journey of ASML, from a small startup in a leaky shed to a technological titan, is a testament to human ingenuity, perseverance, and the power of collaborative innovation. It demonstrates that breakthroughs often come from daring to tackle problems others deem impossible, investing for the long term, and fostering an ecosystem of highly specialized partners. Their story is a powerful reminder that the greatest advancements are rarely the product of a single mind, but rather a symphony of collective effort and shared vision. While the geopolitical implications of ASML and TSMC's dominance are profound, it's crucial to remember that their innovations also drive immense progress for humanity. From medical breakthroughs powered by AI to solving complex scientific challenges with supercomputing, the availability of advanced chips accelerates every field of human endeavor. The machine that controls the world doesn't just enable power, it enables progress, pushing the boundaries of what is possible and expanding the horizons of human knowledge and capability. Every text message, every online purchase, every autonomous vehicle, and every satellite in orbit relies on the chips fabricated by TSMC using ASML's machines. These are not abstract technologies, they are woven into the very fabric of our daily lives, often unnoticed. This makes the security and stability of this manufacturing pipeline a concern not just for governments and corporations, but for every individual who benefits from the digital age. The invisible power is profoundly personal. The current global technological landscape is one of precarious balance. A single company in the Netherlands, ASML, holds the key to the most advanced manufacturing tool, and a single company in Taiwan, TSMC, is the unrivaled master of using it. This concentration of power and expertise is both a testament to specialized innovation and a source of immense vulnerability. The world navigates this balance, seeking both to leverage the benefits of these technologies and to mitigate the risks associated with their concentrated control. As the demand for even more powerful and efficient chips continues to grow, the pressure on ASML and TSMC will only intensify. The challenges of pushing into sub-nanometer nodes are immense, requiring further breakthroughs in materials science, quantum physics, and manufacturing processes. The geopolitical competition will likely sharpen, with nations continually vying for access or the ability to replicate this essential technology. The road ahead is one of relentless innovation and enduring strategic competition, shaping the digital future for all of us. The ability to produce these advanced chips hinges on a fundamental equation: smaller features require shorter wavelengths. This simple truth drove the industry from visible light to deep ultraviolet, and finally to the extreme ultraviolet. ASML's genius lies not just in recognizing this, but in pioneering the seemingly impossible technologies to achieve it. Their EUV machines are the ultimate manifestation of this principle, allowing us to etch patterns at scales that defy easy comprehension, pushing atoms into precise arrangements. The story of EUV lithography is also a lesson in the power of long-term investment and unwavering perseverance. It took ASML and its partners over 2 decades and billions of dollars to bring EUV from concept to commercial reality. Many doubted it would ever work. This kind of patient capital and sustained scientific effort is rare, but absolutely essential for tackling grand challenges. It highlights that true technological leadership is not built overnight, but through decades of dedicated, focused, and often frustrating work. ASML, a commercial company, has inadvertently become a vital component of national security for multiple countries. Its technology is so strategic that governments actively intervene to control its distribution. This places ASML in a unique and challenging position, balancing commercial interests with geopolitical pressures. Their machines are not just tools for profit, they are instruments of national power, illustrating how deeply intertwined technology, economics, and security have become in the 21st century. It's a heavy burden for a technology company. Similarly, TSMC's rise to dominance wasn't just about technical skill, but also strategic patience and a singular focus. While competitors diversified, TSMC remained a pure-play foundry, pouring all its resources into manufacturing excellence. This allowed them to outpace rivals, building an unmatched ecosystem of expertise, processes, and a relationship with ASML that created a formidable competitive moat. Their unwavering commitment to the foundry model, combined with an insatiable appetite for the most advanced tools, defined their success. If semiconductors are the brains of our digital world, then ASML's EUV machines are the scalpels and TSMC's fabs are the operating theaters where these brains are meticulously crafted. The entire system functions as a global brain, an interconnected network of innovation, manufacturing, and consumption that shapes human destiny. Understanding this intricate relationship is key to comprehending not just technology, but the very fabric of our interconnected global society. It's a system of unparalleled complexity and importance. The relentless march of progress doesn't stop at nanometers. The industry is now looking towards the angstrom scale, where features will be measured in tenths of a nanometer. This requires even more precise light sources, more advanced optics, and materials science breakthroughs. High-NA EUV is the stepping stone, but beyond that lies an entirely new realm of physics and engineering challenges. The boundaries of what is physically possible are constantly being redrawn, fueled by the insatiable demand for more computing power. Even semiconductor giant Intel, once the undisputed leader, has fallen behind TSMC in advanced manufacturing. They are now investing tens of billions to catch up, building new fabs and embracing ASML's EUV technology. This monumental effort highlights the enormous capital, expertise, and time required to compete at the leading edge. Intel's journey illustrates that even with immense resources, the gap created by ASML and TSMC's combined innovation is incredibly difficult to close, underscoring their unique, almost unassailable, position. The immense scale and precision of advanced chip manufacturing come with a significant environmental footprint. Fabs consume vast amounts of electricity, much of it from non-renewable sources, and require billions of gallons of ultra-pure water. While companies like TSMC and ASML are investing in sustainable practices and renewable energy, the sheer energy and resource intensity of their operations present an ongoing challenge. Balancing technological progress with environmental responsibility is a critical consideration for the industry's future. Despite the high degree of automation, the human element remains indispensable. Thousands of highly skilled engineers, physicists, chemists, and technicians at ASML and TSMC work tirelessly, monitoring systems, refining processes, and solving complex problems that arise daily. Their collective knowledge, built over decades, represents an intellectual capital as valuable as the machines themselves. It's a symphony where human expertise guides and optimizes the automated dance of light and silicon, proving that even in the most advanced fields, people are still at the core. The global semiconductor ecosystem is built on a complex web of trust. Chip designers trust TSMC to protect their intellectual property and execute their designs flawlessly. TSMC trusts ASML to deliver and maintain the most advanced lithography tools. Governments trust these companies to maintain supply chain stability. This trust is now under strain from geopolitical tensions, forcing a re-evaluation of long-standing relationships and raising questions about the future of global technological cooperation. Erosion of this trust has far-reaching consequences. ASML's EUV machine is more than just a piece of industrial equipment, it is the heartbeat of modern innovation. It enables the creation of chips that drive every new technological leap, from quantum computing to personalized medicine. Without this machine, the pace of progress would slow dramatically, potentially altering the trajectory of human civilization. Its existence and continued development are critical to everything we aspire to achieve in the digital age, a silent engine powering our collective future. The potential consequences of a failure in this critical supply chain are almost unimaginable. If ASML's production of EUV machines ceased, or if TSMC's fabs were to halt operations, the global economy would face an immediate and profound crisis. Industries would grind to a halt, technological development would stagnate, and national security capabilities would be severely compromised. The very infrastructure of our interconnected world depends on the uninterrupted flow of these ultra-advanced chips. The cost of failure is global devastation. Taiwan finds itself in a unique and precarious position. Its technological prowess, encapsulated by TSMC, offers both protection through this silicon shield and simultaneously makes it a highly coveted target. The island's economic prosperity and global standing are inextricably linked to its semiconductor industry. Navigating this dilemma, balancing economic growth with national security, is a constant and defining challenge for Taiwan, underscoring the profound real-world impacts of this highly specialized technology. What ultimately unites ASML and TSMC is an extreme engineering mindset, a relentless pursuit of perfection, a willingness to invest in seemingly impossible solutions, and an unshakable belief that every problem has a solution, no matter how complex. This ethos has allowed them to push the boundaries of physics and material science, turning theoretical concepts into tangible machines that change the world. It's a culture of innovation that drives progress far beyond simple market demands, towards true technological mastery. The era ushered in by extreme ultraviolet lithography and TSMC's manufacturing dominance is not merely an extension of previous technological trends, it is a fundamental shift. It represents a new level of precision, integration, and complexity that underpins the next generation of computing and intelligence. We are at the dawn of an era where the tiniest components hold the greatest power, and the ability to craft them defines global leadership. This technology is not just important, it is defining. Behind every $200 million machine, every nanometer etched, and every strategic decision, there are thousands of dedicated human beings. Their decisions, their collaborations, and their relentless innovation are what truly control the world, not merely the machines themselves. The story of ASML and TSMC is, at its core, a human story, a story of ambition, scientific curiosity, political strategy, and the collective will to shape our technological future, one atom-thin layer at a time. It is a profound testament to human endeavor. This entire ecosystem highlights an undeniable truth: global interdependence. No single nation or company possesses all the pieces required to build the most advanced chips. The unique light source from one country, the ultra-precise optics from another, the manufacturing prowess from a third, all come together in a delicate, yet powerful, symphony. This interdependence can be a source of strength, fostering collaboration and shared progress, but it is also a profound vulnerability when geopolitical tensions rise. The world is truly connected at the atomic level. Securing the future means not just securing access to these machines, but also fostering the environments that produce them. It means investing in science education, promoting international collaboration, and managing geopolitical risks with foresight and diplomacy. The fate of our digital world, and much of our future prosperity and security, rests on the continued, uninterrupted functioning of this extreme lithography ecosystem. It is a responsibility that falls on the shoulders of governments, industries, and indeed, all of us. The competition for dominance in extreme lithography is a silent battleground, waged not with tanks and missiles, but with lasers and mirrors, scientific breakthroughs and strategic alliances. It's a testament to the fact that in the 21st century, the most critical conflicts are often fought in the realms of technology and economics. The $200 million machine that controls the world stands as a stark reminder of where true power now resides, shaping the destinies of nations and the daily lives of billions, far from any traditional front line. The entire endeavor of EUV lithography was a leap of faith, backed by decades of rigorous scientific inquiry and engineering brilliance. From the initial skepticism about tin droplets and reflective optics to the perfected systems in use today, every step required overcoming immense technical barriers. It's a story of how pure scientific curiosity, combined with pragmatic engineering, can create technologies that were once relegated to the pages of science fiction. The journey itself is as impressive as the destination. To fully grasp the magnitude of ASML's achievement, consider this: the features etched by EUV are so small that a single human hair is roughly 7,000 times wider than a 7-nanometer transistor. If a chip were scaled to the size of a city, these transistors would be smaller than a grain of sand. This mastery over the scale of tiny is what defines the modern era, allowing unprecedented computational power to fit into devices we hold in our hands. It's truly a marvel of microscale engineering. Both ASML and TSMC exemplify the power of extreme focus. ASML chose to specialize almost exclusively in lithography, while TSMC committed solely to the pure-play foundry model. This singular, unwavering focus allowed them to allocate resources, talent, and strategic vision towards mastering their respective niches to an unparalleled degree. In an increasingly complex technological landscape, their stories suggest that deep specialization, rather than broad diversification, can lead to foundational dominance and irreplaceable strategic value. The silicon shield is not a static concept; its effectiveness will evolve with global dynamics. As other nations attempt to build domestic chip production capabilities, Taiwan's unique leverage may shift, but its lead in the most advanced nodes will likely persist for years. The future of the silicon shield depends on continued innovation, geopolitical stability, and the world's enduring reliance on Taiwan's manufacturing might. Its strength is a constant calculation, a testament to the intertwining of technology and fate. Ultimately, the $200 million machine from ASML and the manufacturing prowess of TSMC represent the invisible hand of technology, guiding the progress of our world. They are the silent architects of our digital future, shaping economies, influencing politics, and accelerating scientific discovery. Their story is a powerful reminder that the most profound forces shaping human civilization often operate at scales imperceptible to the naked eye, hidden within pristine cleanrooms in the heart of ultra-complex machines. We rarely see them, but we feel their impact everywhere. At its very core, this is a story of unprecedented collaboration. No single company, no single nation, could have achieved the marvel of EUV lithography or built TSMC's manufacturing empire alone. It required an intricate dance of international partnerships, shared research, and a global supply chain built on trust and mutual expertise. This spirit of collaboration, even amidst geopolitical rivalry, remains vital for tackling the next generation of technological challenges and ensuring the continued progress of humanity. The legacy of ASML and TSMC will be etched into the very fabric of our digital civilization. They have not merely created products, they have created the foundational technology that enables countless other innovations. Their impact is generational, affecting how we communicate, work, learn, and live. The $200 million machine, born from daring vision and relentless execution, stands as a monument to human ingenuity, a testament to what is possible when science, engineering, and strategic purpose converge to build the unseen architecture of the modern world.